Recording in progress.
Great. So today we're starting spectral sequences. Or no, we're not doing that. We're starting derived categories. Goodness. I don't know exactly what I'm going to get to tomorrow. But for today, I just want to just talk about what it is. And maybe tomorrow we can say something about why we care. But the construction is a little involved and it's worth talking about. It's interesting. I think at least once we should sort of carefully see something. And then in the future, you can intuit it or whatever. I don't know. Okay. So roughly speaking, what is the derived category? It's some kind of analog. It's some kind of algebraic analog to the homotopy category in topology. So roughly speaking, start with an abelian category A. So start with an abelian category A. And then there's a few steps you need to take to get the derived category D of A. So obtain the derived category by the following steps, which I'll just write the outline. So the first one is to take A and form the complexes of objects in A. So that's denoted CHA. These are the complexes of, okay, I should say this is the category of whether it's chain or cochain. We typically just take cochain just because we like cohomology. So let's just say cochain complexes of in A. Yeah. And then the next step is to take a quotient of these complexes. So from CH of A, take a quotient by what? Well, I'll talk about that later. To get this so-called homotopy category K of A. So the homotopy category K of A. Okay. And then the last step is from K of A, you have to localize to get the derived categories. So localize at the quasi isomorphisms to get D of A. And I'll define quasi isomorphisms later. But I want to start from the beginning in this outline and fill in the details, or the details that I think are relevant. There's a lot of other details that are more technical that I'm not going to talk about. Okay. So we start with, well, okay, we talked about chain complexes or cochain complexes already. So I'll just start with how to get the homotopy category. So K of A. So what is this category? This is, so the objects are still cochain complexes, but the morphisms are different. So I'll just describe it in this way. So I say hom from A bullet to B bullet consists of what? Well, they're the chain maps from A to B such that, or not such that, but you define this equivalence relation on these chain maps. And the relation is chain homotopy. So this is chain homotopy. That is to say F and G are in the same equivalence class if F minus G is equal to ds minus SD for S well, okay. To summarize, I'll just say degree minus 1. Well, I shouldn't say map, but let's say Sn going from, what was it? It was Cn to Dn plus 1. No. Cochain complexes are increasing, so minus 1. I think when I first introduced this, I had written it for chain complexes. So, okay, we have to flip it, fine. Okay, great.
Isn't it DS plus SD?
I don't think so. We can check after, but I think this is the one.
Wait, surely it's plus. Like, isn't it the same chain homotopy as you were doing before?
Yeah, it should be the same. Okay. Maybe, I don't, okay, my notes are, well, maybe, I mean, I'm using the same document. I could go back, but I don't know what page we define them on.
It might not have any like effect if we said it was plus or minus. But like
right,
without going into
maybe,
details.
Yeah. No. Where did I define? Okay. Oh, it must have been the second day. Oh, plus. Okay, maybe it's minus just because I'm doing this cohomology thing. Okay. Yeah. So probably what Ryan said is right. I think Weibel flipped it around at some point and I didn't notice. Okay. Okay. But good catch, yeah. So good. Okay, so there is an objection. So if I have, now that the morphisms are equivalence classes, you may raise the question like, do these compose correctly? Like if I take two maps and any two equivalence classes that are composable in the right way, does this now define a new morphism? Like you have to unpack that, and so it's a sort of classical exercise to show that if you have two chain homotopic maps and you pre-compose something or post-compose something, they still end up being chain homotopic. So there's like this ideal structure or whatever you want to think about. It works like that. So, okay, you have to check that composition is well defined. Okay. Good. So now, what do the isomorphisms in this homotopy category look like? So isomorphisms in Ka, well, they are the chain homotopy equivalences. So if I have A bullet and B bullet, and I have a chain map F like this, then F, I write the equivalence class of F is an isomorphism in K, Ka, if, okay, I guess I mean if and only if, right? If there is a a G for which FG, GF are the same, they form the same class as the identity, and I'm just gonna write it twice. Well, okay, which identity is it? Well, the first one is, so G will go this way, right? So if you do G first, then it's id B bullet, and then id A bullet, respectively, fine. And so if you unpack this, this is just to say that FG is homotopic to id B, and then GF homotopic to id A, which is to say they're F is a chain homotopy equivalence of the complexes, ... Fine. Okay, and so then what happens is that the cohomology functors that we get for chain complexes, they pass to well-defined functors on Ka. So Hn define functors on Ka. So functors Ka to A. Cool. Great. So I mentioned this word quasi-isomorphism. I'll define it now. So a chain map F, so A to B, F, is called a quasi-isomorphism, which is usually, I mean, you might read quism or quiz, something, some substring. I forget which. Or a Q-iso. Q-iso is something I've seen once or twice. So it's a quasi-isomorphism of complexes if the induced maps on cohomology, so Hn A bullet to Hn B bullet. So this is again just the induced map F. On cohomology, these are all isomorphisms. Oops. Isomorphisms, goodness. And so, okay, some examples. So here's like the most, or like the first example, or the only example I'm going to give, which we've seen before. So, e.g., so projective resolutions. You can think of them as quasi-isomorphisms, really. So if I have something like this, P2, P1. Oh, okay. So for projective resolutions, I'm going to be writing down a chain complex. So really, here you can also think about homology as well, but whatever. It's the same definition. Everything is, whether you co or not, it doesn't really matter. Everything is symmetric in some sense. P2, P1, P0, and then this epsilon map. So if I have a projective resolution like this, we can instead think of it like this. So ... P2, oops, and then P1, P0. But instead of going to A, you can stick on a 0 here and just keep going with zeros. And then below it, stick in a bunch of zeros, and then in degree 0, put A, and then more zeros, like this. So, okay, and then this epsilon map goes this way, right? Okay, and then these are all the zero maps. Great. So this defines a quism. Can you see this? So on the bottom, the cohomology of the bottom sequence is just A concentrated in degree 0, and then the same thing in the top row. So cool. And then this similar for injective resolutions. So given something like this, you have 0 to B to Q0, Q1 to Q2, and so on. You can get, now you put zeros on the left, Q0 here, Q1, Q2. Down here, you put more zeros, put B here. I'll call this map eta maybe, doesn't matter. And then this is the QUISM as well. Not bad, but this is like a good way to think about projective resolutions. They're just like a different complex that sort of captures basically the same information as A, but like in terms of, or you know, a resolution just captures the information of what it's resolving, but sort of homologically or cohomologically in some sense, I guess. So it's an interesting perspective, I think. So okay, here is an interesting observation. So if f from A to B, which I might have made this observation before, it's that if f is a chain homotopy equivalence, then f is a QUISM. And you may ask about this direction. Are all QUISMs chain homotopy equivalences? It is not always the case. It is if you're in a nice situation, like if you're over a field, if everything is done over a field. But I should probably give you guys a counterexample. So at least the counterexample I have here is in the homology setting, but just look at it from behind the screen or something. It's the same. So counterexample. So I'll put in quotes homological or whatever, because I guess I'm thinking of this as a bunch of chain complexes. So I'll have 0 and then 2 copies of Z, and 0. This is the multiplication by 2 map. And then the second complex is 0, Z, or sorry, 0, and then Z mod 2Z, and then 0. And then this map is just the 0 map, here, 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 and then here is just the projection map. And so, yes, you get isomorphisms on homology, so you get isomorphisms on homology. G, oh dear. But it's not a chain homotopy equivalence. Why is that? Well, you have to be able to produce a G going back this way, right? But sort of the problem is that how are you going to define a map from Z mod 2Z to Z that isn't just the 0 homomorphism, right? So there are no non-zero maps going this way, Z mod 2Z, 2Z. So that's why this is bad. So, okay. Cool fact. Right, so far we've gotten to the homotopy category. Now we have to localize, but localization is sort of, it's a process, and we should talk about it some before going to finish it up and or whatever. So we'll take a quick detour to just talking about localization of categories. Am I on time? Good. So this is spiritually very similar to localization of rings. Process is similar. So I'm going to write down a lot of stuff and it'll feel very familiar if you've seen localization before. So let S be a collection of morphisms in a category C. And so collection here, I may want to stick some more adjectives here. So preferably a multiplicative system. Right? Like in algebra, you want to localize with nice sets if you can. Here I've written collection. I'm going to ignore all the set theoretic issues. We're just going to do everything sort of formally. So yeah. Okay, so I have a bunch of morphisms, and then I'll define at least the universal property for this, and then shortly I will give you a concrete description of this, but I would like to do it if so I will show you the concrete setting when we're localizing with the multiplicative system, but you can do this in general, and it looks like this. So there's S inverse C, that's the localization of C with respect to S is the, and so then it's if, so there is a functor. So I guess this couldn't happen all the time. You have to be able to do this. So Q from C to S inverse C such that two things happen. One, Q of S is an isomorphism for all S in S. Or an iso in where? An iso in S inverse C for all S in S. And then the second thing is that there's this universal property if F also is a functor from C to S inverse C that sends S in S to isomorph. Okay, so sends any S in S to an isomorphism in S inverse C, then this functor should factor through uniquely. It should factor uniquely through Q, and yeah, that's I mean it's the usual universal property that you would expect. So then F factors uniquely through Q. So what's the upshot? S inverse C is unique up to equivalence of categories. Okay, fine. This is not super surprising, I guess. But if we want to have a better description, like an actual concrete description, we need to pick our S carefully. So here is multiplicative systems. So multiplicative systems. S, they are also called localizing systems or localizing classes. So these are collections. So I want to match the account. So this is a collection of morphisms in C such that a few things should happen. So the first thing is that S is closed under composition. So this is like multiplication. And specifically what we should have is all identity maps in C are in S. So that's part of this. Okay, the next thing that should happen is this so-called ORE condition. I don't know who this ORE is, but there's this interesting condition which will basically allow us to compose after we localize. So this ORE condition comes in two forms. They're like symmetric, but so I'm going to draw a few diagrams. So provided the blue parts, there exists a red in the following diagrams. So you can start with something like this. So you start with Z, X, and Y, three objects. And then from Z to Y, start with T and S, and then let X to Y just be any G. And then what you should be able to do is then you can form an object W. You can get arrows this way. This one is S, which is in S. And then here you can just pick out an F. And then this diagram commutes. So what is the slogan for this is that it's T inverse G is equal to F S inverse. So, I have a laser pointer. Let's do that. So T inverse G. So oops. So start with G, then go up this way. This thing agrees with this thing, sort of, right? And then the flipped version of this also should hold. So I start with W, Z, and X. And I start with F. I start with S and S. Then there should exist a Y going here. Oops. And two maps going into Y. I'll call this one T. T has to be an S. And then this one is G. And this will make the diagram commute. And then again, you get this Fs inverse is equal to T inverse G thing. So again, going, so Fs inverse. So this is the same as this, morally speaking, I guess. And then the third condition is this so-called cancellation property. So if F and G have the same source and target, so if I have something like this, so X and Y, this is F, this is G, then I have this interesting condition. Then SF equals SG for some S and S. So if there exists an S for which this equation holds, this is equivalent to this equation holding for some T. So FT equals GT for some T in S. And of course, S has to have the right domain and T has to have the right codomain for all of this to, of course, to compose, right? But this condition will hold. But of course, the most important condition here is this ORE condition. So this will allow us to talk about composing whatever that is. So, okay, now I'm ready to talk about an explicit description of the localization when we have a multiplicative S. So if I have a multiplicative system S, then S inverse C is the following. So the objects are the same as in C. So same objects as in C. And the morphisms are, this is the interesting thing. These are equivalence classes of roof diagrams. So roof diagrams. So they look like this. So if I have A and B, so something like this, then there's a third object C up here. I draw two arrows like this. So it looks like a rooftop. The morphism on the left is S, which is an S, and then it can be F on the right for any F, whatever. And so you're supposed to think of this as this left fraction, which is left fraction F S inverse. Right, so you think, so this, like this, you put it like this somehow. At least visually, that's what you think of. So that is to say this Fs inverse labels this entire diagram, and this is in AB. Okay. And so now what is this equivalence relation? Right, so Fs inverse is equivalent to GT inverse if, so now again in red I will complete the diagram. The red stuff. So okay, this is separate from this. So, okay, I should start by drawing both of the diagrams for Fs inverse and GT inverse. I'll draw them at the same time. So I have A and B, and then maybe for the first one, I'll denote the peak by C and this one by D. So the first one, this is S, and this is F. And the second one, this is T, this is G, right? Yeah. Maybe I'll put the T up here. Fine. So I need to be able to produce something like this. And what letter haven't I used? E. Okay, E. And then there's S prime and T prime such that, so everything commutes. And in particular, this S prime and this T prime belong to S. And yeah, so that's the condition for equivalence classes. So yeah. And I'm not gonna bother by putting brackets on the equivalence classes or whatever. They're just, yeah. Okay, is this okay? Good. So these are the morphisms. Now, how do you compose them? That's where this or condition comes in. So composition. Let's put Fs inverse in AB, and then what have I called this one? GT inverse in BC. Great. So I'm gonna have to draw like this M-shaped thing. So I have A down here, B in the middle, and C over here. And then for this first one, I will have something like this, right? With a D up here, maybe. This is S, this is F, Then over here, a similar thing. Say E. This is T. Make this F very clear. This is G. Okay. So use the ORA condition to get the red part. So remember, the ORA condition lets you complete this sort of part of the diagram, right? I can complete it by putting two maps like this, and then there's some object. Which letter have I not used? F. So because T is an S, the one parallel to it, which I'll just call S prime, is also an S. And then over here, I'll just call this like T prime or something, whatever it ends up being. And so notice that this S prime is an S, right? So then that means if I take this composite, right? This highlighter is a little bright, but yeah, I guess, okay. Hopefully this is still visible, but you just take the top part of the triangle and that defines a new, that defines the composition. So take highlighted part as the composition. And, you know, I guess maybe if we're curious, what is it labeled by? This is, so I have G, T prime, and then I am inverting S prime like this or something. I mean, you can write whatever you like down there. Fine. So you may have an objection. Is this well defined? Of course, everything, all these morphisms are equivalence classes, right? So you have to check for well definedness. Composition. So okay, the composition, I should say, this is the composition. Fs inverse compose. Wait, no, which way am I going? Start with Fs. Goodness. And then apply GT inverse. So it's kind of like fractions in some sense. You get this like common denominator or whatever. Okay. So now what I mentioned that the localization should come with this functor C to S inverse C. So what is Q from C to S inverse C? Well, on objects, it is the identity. But on morphisms, what should it do? So then F is sent to, so okay, F from, oh, okay, I'm gonna need some more space, I guess. I'll move this here. So F from X to Y is sent to the roof diagram. So, okay, well, I have X and Y here, right? The only way I can make this into a roof diagram is to put the identity here. Oops. And of course, I mentioned that all of the identities are in S, so this really is something you can do. So good. So that's what that looks like. And so does this actually do what we want it to do? Meaning if F is in S actually is, so this is F id inverse. Is F id X inverse invertible? It is. You have to, I mean, you do the procedure from above, right? So I take the morphism I started with, like this. This is id X. I just won't write the ids down. There are going to be a lot of them. This is F. I can also like flip it and do something like this. and then the actual Ore square or whatever this is supposed to be, I can just put X here and then identities again and again, and then this will commute and it will do everything you want it to. So, and you can of course mirror this, so you really get invertibility. So dot dot dot. You can imagine it. It works out. So this is the highlighted part is the identity on X in the new category after localization. Cool. Okay. So now that we have a description of the localization, now I can just wave my hands and say, okay, to wrap up, this D of A is so QIS inverse KA. And this QIS is the set of, not set of, the collection of quasi isomorphisms. So you need to check that QIS forms a multiplicative system. In K of A. But more interestingly is that QIS is not a multiplicative system so one layer behind K is just chain complexes, so CHA. So this is true. And I will actually show you a simple counterexample. Well, I hope it's simple. I didn't check all the details. I hope it's like easy. I didn't, I thought about it for like a few minutes and I don't know if I'm missing something obvious or missing something subtle. But okay, here it is in abelian groups, say. So in AB, we cannot localize CHAB at QIS since one of the Ore conditions fail. Since Ore conditions fail. Okay. So okay, maybe so I want to try to do this Ore square thing for certain complexes of abelian groups. So let's take B bullet to be just Z and Z. This is just the identity map. So I guess I'll just put identity here. And then every other map is 0, but I'm just not going to write that down. And then the C bullet is, let's say 0 into Z, and then everything else also 0. So then if I, okay, think A bullet is equal to the 0 complex, but so if I have the 0 complex here, and I have C bullet, where do I want to put it, like here? C bullet, I can put B bullet down here. So this one is this map down here is the, wait, that's weird. Yeah, 0 complex here. This one is the 0 chain map. And then this one is just, so C bullet is 0 and Z, right? So 0 into the first copy of Z is a 0 map, and then the identity map. So it's the map you think it is. And so, okay, I want to complete it. So I should have something here, and I should have something here. Oh, and I should say that this map here is a quism, right? What is the homology or what is the cohomology of B bullet? It's all 0, right? Because I just have an isomorphism in the middle somewhere. So everything, all the cohomology groups are 0. So, and this is the same as for the 0 complex. So, the 0 map constitutes isomorphisms of 0 modules, right? So this is a quism. And if I want to do this or a square thing, this also needs to be a quism. So needs to be a quism up here. And also this has to commute, right? So if I start from up here and I go down and then to the right, well, then the total composite will be the 0 morphism, right? So the same thing has to happen up here. I have to get the 0 composition that way. But at the same time, this thing needs to be a quism. But the cohomology of C bullet is just Z somewhere. I don't care what degree. I mean, you get one cohomology group, and that's Z. So you have a non-zero cohomology in C bullet. So this, whatever this object you wanted to put here, must also have, so it must have the same cohomology, right? Which is just Z concentrated somewhere. So this map on the top couldn't be the 0. It couldn't be the 0 morphism. And also this map here is not 0, right? So I think this is the contradiction. Like you couldn't do this, right? So this should be the counterexample. Yeah, so I think that's all I wanted to say today. Yeah, so a little early, which is fine. But yeah, I will stop recording. I will see you all tomorrow.